The idea of creating super-heavy artillery like the Dora did not arise out of nowhere. It resulted from a combination of technological, military, and political factors that took shape in Europe from the late 19th to the first half of the 20th century. The first factor was the experience of sieges and positional warfare in World War I, 1914-1918. In trench and fortified battles, standard field guns often proved powerless against deep concrete shelters, armored casemates, and reinforced concrete batteries. German and French engineers faced the need to break increasingly durable fortifications. The solution was sought in increasing caliber and the armor-piercing energy of munitions. Precedents, large howitzers and siege mortars, including the famous Big Bertha, demonstrated the effectiveness of large calibers against stone and concrete works, but also revealed limits. Conventional designs were constrained in range, power, or mobility. The second motive was the evolution of fortifications in the interwar period. By the 1930s, fortification lines had become ever more powerful: multi-layered concrete belts, underground casemates with armored turrets, artillery shelters, and deep engineering works. Modern defenses were designed to withstand prolonged, heavy bombardment. Ordinary divisional artillery could no longer reliably neutralize such targets. To break through, a weapon was needed that could disable deep concrete slabs and massive armored barriers, hence the demand for an ultra-powerful siege gun. A third factor was technical and industrial feasibility. Rapid technological progress in heavy engineering and metallurgy made it possible to produce very large barrels and massive shells. Industrial giants like the Krupp firm had, by the late 1920s-1930s, accumulated experience manufacturing large calibers and railway platforms. The railway infrastructure offered a way to transport heavy sections, and the very concept of a railway gun seemed practical. Rails provide support for enormous weight, and modular assembly made it possible to move parts through factories and along lines to the assembly site. The political strategic motive was also important. With a new war looming, German command sought advantages on fronts where suppressing fortresses or powerful defensive nodes might be required, for example, on the Eastern Front or in preparations for operations against metropolitan centers protected by fortified lines. Possessing a supergun was also meant to produce a psychological effect, intimidating the enemy, demonstrating technological superiority, and serving as a tool of propaganda at home. No less significant were doctrinal and bureaucratic reasons. Artillery staffs and engineers tend to solve problems by increasing power. If existing systems are insufficient, the logical step is to ask for even more. For large enterprises, this was an engineering reputation challenge. Accomplishing the unthinkable was prestigious and profitable. Fears of repeating World War I scenarios, when failure to suppress fortified positions quickly proved costly for the attacker, also played a major role. Finally, practical constraints, simultaneously a motive and a brake, must not be forgotten. Designing a supergun was a response to a real problem, but awareness of its limitations, dependence on rails, slow deployment, enormous logistical and ammunition needs, formed during development. Nevertheless, in the 1930s the combination of military needs, technical capabilities, and political will made the idea viable, at least as single specimens. Dora became a logical, if extreme, consequence of these premises, an attempt to answer a new form of fortification defense through maximal artillery power, even at the cost of great complexity and high expense. The super heavy gun project did not begin with a single sketch but with a lengthy chain of engineering calculations, each imposing constraints on the others. Ballistics dictated the design of the barrel and charges, recoil and support structures determined the geometry of the carriage and the requirements for the rail platform, and ammunition requirements influenced manufacturing technology and storage. At the center was a team of engineers, ballisticians, metallurgists, mechanical designers, and railway specialists, typically within a large firm like Krupp, where calculations, drawings, and field tests were carried out in separate departments. Ballistic calculations. The first step was to determine the required caliber, shell mass, and muzzle velocity, values that govern penetration, range, and charge requirements. Engineers computed trajectories for different ammunition types: heavy armor piercing, heavy high explosive, lightweight long range, accounting for air resistance, barrel whip during firing, dynamic bending, and bore heating. For large calibers it was crucial to consider pressure distribution along the barrel. An incorrect bore profile could cause localized damage or premature wear. Thus pressure profiles were developed, optimal diameters and wall thickness were selected, and rifling parameters, depth, twist rate, were chosen to stabilize the projectile. Recoil and support structures. The recoil energy of such a massive shell was colossal and had to be absorbed without destroying the platform. The solution was combined recoil systems, a long recoil stroke on the carriage with massive hydraulic or hydropneumatic/spring oil buffers and recuperators distributing load through the support frame. Simultaneously, chocks and struts were designed to transfer part of the reaction into the ground and rails, via heavy support plates and bracing structures. The railway mounting provided multi-axle bogies for transport and a separate stationary firing platform. On the selected site the rails were laid on reinforced sleepers and additional support beams, with anchors and support trusses installed around to prevent the reaction from destroying the track. Secondary effects were incorporated: vibration, shock waves through nearby structures, and the need for precise elevation and traverse control. Ammunition and semi-fixed components. Ammunition for such a gun was a separate engineering challenge: thick-walled bodies, to withstand acceleration and chamber pressures, optimal ogive shapes for penetrating concrete and armor, and internal arrangements for charges and fuses. Shells were made from high-strength steels, heat-treated, and internally designed with compensating cavities and pinned joints for stability during transport. Tandem concepts were used: heavy armor-piercing shells with delayed fuses for penetration and detonation inside the target, and large he shells for destroying external structures. In parallel, charge cartridges were developed, complex, combined propellant charges, sometimes packaged in multiple increments to regulate muzzle velocity. All this required special handling, dedicated platforms, craneage for loading/unloading, and careful procedures when placing charges into the loading machine. Barrel and major component manufacturing. Given the dimensions, the barrel was not produced as a single monolith on ordinary shop machines. A sectional approach was used. Individual ring or cylindrical sections were sized, each undergoing forging/stamping or machining, subsequent calibration, internal boring, and rifling. Bores of such diameter required special long-travel boring machines and controlled pull-through rifling to prevent misalignment. Sections were joined with flanged or tapered joints with high-precision centering, and subsequent thermal shrink-fit/controlled bolting joints were rigorously tested for seal and strength. After final assembly, the barrel underwent proof firing and tensile checks, with deflection and microcracks recorded. Carriage, platforms, and armored elements. The carriage and support trusses were produced from thick plate and structural steel with subsequent heat treatment and stiffening ribs. Large subassemblies required heavy welds and post-weld straightening. Each major part was lifted and installed with heavy cranes and special assembly frames. All moving mechanisms, traverse gear, elevating screws, were built to high precision and repeatedly endurance tested. Shell and component production. Shells moved through processing stages: forging the body, boring, heat treatment, grinding, and applying the driving band profile to engage the rifling. Inside, fuses and explosive trains were installed. Large he shells received layered charges and protective liners. Each shell type underwent ballistic testing at a dedicated range to validate body integrity at firing and penetration into reinforced concrete targets. Production logistics. All operations required coordination. Heavy sections were transferred by rail to specialized assembly sites where barrel and carriage were mated. Assembly and test stands were equipped with lifting gear rated in the hundreds of tons, rigs to verify recoil systems, and support stability. Plants documented quality, metallographic analysis, ultrasonic and radiographic weld inspection, and fatigue testing before accepting assemblies. Control and refinement. Feedback existed at all stages. Results of live-fire trials could require adjustments to recoil systems, damper placement, or even projectile shape. The design evolved iteratively, drawings were updated, processes improved, until a workable combination of ballistics, strength, and throughput was achieved. The Schwerer Gustav gun was deployed for combat in Crimea in 1942 as part of a heavy artillery unit of the Wehrmacht and was used during the prolonged siege of the fortified city of Sevastopol. Transport, assembly, and preparation for action amounted to a massive engineering logistical operation: more than 20 railcars with barrel sections, carriage, cranes, and auxiliary equipment, plus significant engineering manpower to prepare a reinforced rail spur and firing position. Assembly and commissioning took several weeks. By the start of firing, coordinated efforts of artillerymen, engineers, and support personnel were required. During the Sevastopol campaign, the gun was employed against specially selected, high-resilience targets, large coastal and land artillery works, concrete casemates, underground depots, and fire control nodes. Fire was delivered at carefully mapped coordinates with support from spotters, and aerial reconnaissance firing solutions were tailored to specific tasks, piercing multi-meter concrete decks and detonating vulnerable infrastructure stores. In the Crimean fighting, Schwerer Gustav fired several dozen rounds at pre-designated targets. Recorded outcomes included serious damage and destruction of individual batteries and depots, including facilities protected by substantial concrete layers. Within the operation, isolated salvos were periodically employed as a means to breach specific sectors of the defense and to eliminate especially durable fortifications. Operation of the gun in combat was accompanied by substantial technical and organizational constraints. Each firing position required reinforced supports and bracing structures, expansive ammunition depots, and constant protection from air strikes and sabotage. The time needed to prepare and bring the gun into action made its use sensible only in pre-planned operations against static, heavily fortified targets. Moreover, intensive firing accelerated barrel wear, necessitating a spare tube and shipping worn parts back to the factory for remachining. These limitations defined both the operational niche and the rarity of the supergun's combat employment. After active operations around Sevastopol ended, one unit was documented as moving to northern theaters. Sources mention deployment or preparations near Leningrad and plans for possible use in other major operations. However, direct confirmation of large-scale combat use in these regions is absent or contradictory. The gun either did not conduct significant firing, or its employment was cancelled due to changes in the operational situation. Documents indicate that such a powerful asset was slated for destroying especially resilient fortifications elsewhere, but for tactical and logistical reasons these plans were not always carried out. The final episodes related to the fate of Gustav/Dora reflect the limited combat employment of this class of weapons. As the final phase of the war approached and Soviet forces advanced, the Germans dismantled or destroyed components to prevent capture. Evidence exists of disassembly or disposal of remnants in the rear. In archives and post-war historiography, cases of actual use are chiefly reduced to the 1942 Sevastopol operation, while other mentions of deployments more often concern plans, movements, and preparations that did not culminate in mass firing. The information presented is based on consolidated historical sources and reports on the gun's operation during 1941-1945. For detailed academic treatment of each episode, operational journals, technical dispatches, and Krupp documents are available in relevant archives and specialized studies on artillery history and fortification warfare. Assigning personal names to machines, guns, and large technical systems is far from unique and has deep cultural, psychological, and organizational roots. In the case of the German supergun, the tradition of naming heightened the perception of the weapon not merely as an impersonal tool of war, but as a personified symbol of engineering prowess and national prestige. A name gives an object character, makes it visible in public space and in the memory of participants, from shop workers to senior commanders and journalists. Such naming performs several functions at once: practical, symbolic, and propagandistic. The practical function lies in easing communication. Instead of a cumbersome catalog designation, serial numbers, factory indices, a name serves as a short and unambiguous reference in reports, technical documents, and everyday crew talk. For workers and engineers who spent months in the shops and on assembly sites, the name made the result of their labor tangible. "We assembled Dora, Gustav is ready for trials," sounds different than the dry factory unit number. The symbolic function runs deeper. In European, and particularly German, techno-culture of the early 20th century, technical creation was seen as a realm of high craftsmanship and national pride. Assigning a name, especially one associated with prominent industrialists, members of industrial families, or engineers' close relatives, meant personalizing the achievement. The product was perceived not as impersonal output, but as the fruit of human will and intellect. The name linked production and result, creating a narrative. Not just a gun was built, but Gustav/Dora was created, conveniently used both within the enterprise and externally. In the realm of propaganda, names of high-powered specimens helped craft a legend of technological superiority. Illustrations, reports, and official communiques could refer to Gustav or Dora as symbols of collective effort and visible proof of industrial might. For the civilian audience and frontline personnel, this served as moral stimulus, demonstrating that we have such developments reinforced belief in technical superiority and the invincibility of the war machine. The fact that the name was easy and human aided the images spread in newspapers, photo albums, and veterans' accounts. Psychologically, the name also affected the crew and technicians. For people working long hours with large jointed sections, cranes, and fine adjustments, personification reduced alienation from the object of labor, creating a sense of responsibility and pride. This emotional bond could raise procedural care, since one's own piece was not merely a mechanism but a symbol of the team's mastery. Simultaneously, the name could reinforce ritualization. At station acceptance or the first shot, there were formal words, photographs, and reports mentioning the gun's name. From the enemy's and neutral observers' viewpoint, the name acted as psychological pressure. News that the opponent had deployed Dora sounded like the appearance of a monster, and in war chronicles and press releases this worked as intimidation. Historical examples show that named giants were sometimes as much concessions to propaganda as to combat needs. Their mention in the news was used to amplify perceptions of technological superiority, even when practical value was disputed. Finally, name and symbolism fostered meme tics, legends, jokes, folklore descriptions, and artistic images. After the war, stories about Dora and Gustav entered memoirs, chronicles, and research literature where facts intertwined with myths. Personification eases the transformation of a technical object into a cultural artifact. The gun is depicted on posters, described in books, and included in eyewitness accounts, thus the name becomes a key to preserving memory. It is important to note that naming was often accompanied by official caveats. Manufacturers and the military could use both factory designations and popular nicknames. At times the same item bore multiple names, depending on context, technical indices in field documentation, a memorable name in the press. In this sense, Dora was less an official catalog name than a socio-cultural marker fixed in oral and written history. The super-heavy railway gun Dora entered history as the largest caliber artillery piece actually used in combat. Yet alongside its symbolic status came a whole complex of problems and limitations that largely undercut practical expediency. These difficulties manifested at every stage, from development and production to deployment and direct combat use. First and foremost, the key factor was the exceptionally high cost. Building a single unit required not only vast expenditures on metal, machining, and ammunition, but also maintaining a massive infrastructure, special track, assembly cranes, auxiliary trains, and ammunition depots. Producing multi-ton shells was as expensive and labor-intensive as building the gun itself. Each shot meant spending resources that, if allocated differently, could have produced dozens of more practical artillery systems. In total war, where resources quickly dwindled, this imbalance became obvious and painful for the economy. The next layer of problems was vulnerability. Despite its massive size and imposing look, Dora lacked adequate protection against air attack. Camouflage and AA cover were used, but the position itself was always a large, visible object for reconnaissance. Aerial photography easily recorded construction, earthworks, and prepared rail spurs. As air power became more decisive, such vulnerability turned the gun into a large and tempting target. Destroying rail approaches or bombing ammunition depots could paralyze its use even if the barrel remained intact. Critical too were slowness of movement and deployment. Transport required an entire train composed of many cars carrying barrel parts, carriage, auxiliary equipment, and personnel. Movement occurred only along pre-prepared rail routes that needed reinforced bridges, sleepers, and track. Even under ideal conditions, assembly took weeks. Meanwhile, in maneuver warfare the front could shift faster than construction finished. As a result, the gun often ended up out of play. By the time it was ready, the situation had changed or the targets were no longer relevant. A corollary was limited mobility. Unlike lighter railway guns or self-propelled artillery, Dora could not quickly change position. It depended on a specific stretch of track where massive supports and fixtures had been built in advance. Moving to a new location required another round of engineering work and lengthy preparation. Thus the gun could be effective only in strictly defined scenarios, prolonged sieges or assaults on fortified cities where the enemy sat still and there was time for unhurried setup. This infrastructural reliance also took another form: total dependence on railways. Without rails, the gun could neither move nor operate. But rail communications were among the most vulnerable elements of military logistics. Blowing track, destroying bridges, or striking junctions made delivery of sections and ammunition impossible. Even local sabotage could delay work for weeks. Unlike aircraft or even heavy howitzers, which could reposition over rough ground, Dora was literally shackled to rails. Another major limitation was low practical efficiency relative to cost. Yes, its shells could penetrate multi-meter concrete and destroy especially durable fortifications, but such targets were few. More often, the same tasks were handled by air bombardment or concentrated fire from more mobile artillery. As a result, the supergun became a tool of narrow specialization, useful only under rare circumstances, yet exorbitantly expensive and laborious to maintain. One must also recall technical operating issues. Colossal loads led to rapid barrel wear. After just a few dozen shots, inspections for cracks and deformation were needed. Replacing the barrel or its parts was extremely laborious and costly. Maintaining recoil systems, elevating gear, and cranes also demanded factory specialists and mobile repair shops. In combat, such resources were not always available, limiting real combat readiness. Taken together, these problems made Dora more a demonstrational weapon than a mass one. It could be used for a spectacular breach on one or two axes, but could not be turned into a regular tool of war. Huge costs, slowness, dependence on rails, and vulnerability to air power negated its destructive force. The symbol of an engineering record became a strategic dead end, which is why further production of such superguns ceased. When the giant Dora entered service, strategic results comparable to turning points in entire campaigns were expected of it. The Wehrmacht leadership and the Krupp concern hoped the gun would be a fortress killer, capable of neutralizing any enemy defensive line. In practice, however, the cost-benefit ratio proved extremely unfavorable. This imbalance was decisive in rejecting serial production. The first element of analysis was the cost of development and operation. Creating the gun required enormous material resources, tens of thousands of tons of high-grade steel, labor from major machine-building plants, special machinery and tools, and the involvement of top engineers and workers. Producing a single barrel took months, and manufacturing shell sets required a dedicated production line. The effort to build one such gun was comparable in labor and costs to producing several dozen tanks or hundreds of medium-caliber field guns. Military leadership soon faced a dilemma: continue funding single wonder guns or shift efforts to the mass equipment the front needed. The next point was limited practical application. Dora could strike only large, immobile targets, concrete casemates, depots, reinforced concrete turrets. There were few such targets. At Sevastopol, several long-term fortifications were indeed destroyed, but as the campaign moved on, such targets were not encountered in similar numbers. In a maneuver war, the gun became useless. Against mobile armored groups or field defenses it was ineffective. Even against static targets, aviation was more often used, heavy bombers and dive bombers that could be deployed faster, cheaper, and with less risk. A third factor was logistical burden. Each operation with Dora became a colossal project, laying track, preparing the site, providing security and supply. Transport needed more than 20 rail platforms. Thousands of personnel were required for service. Such resource concentration inevitably diverted strength from other directions. Moreover, with shortages of equipment and fuel in 1942-1943, dedicating entire trains to a giant gun seemed increasingly unjustified. Vulnerability also mattered. Despite its power, Dora was virtually defenseless against air power. Any enemy raid on prepared positions could paralyze work or destroy surrounding infrastructure. Camouflage and cover were used, of course, but as Soviet and Allied air superiority expanded, the risk grew. While ordinary artillery batteries could change position within hours, Dora was tied to a specific rail section and became an easy target for reconnaissance. Evaluation also considered structural wear. Despite the barrel's colossal thickness and quality steel, accuracy degraded quickly after a few dozen shots. Replacing or repairing the barrel required returning parts to the factory and took months, making operation extremely difficult and uneconomical. A weapon designed for a miracle effect proved capable of only a limited number of salvos before becoming more of a burden than a tool of war. All these factors led command to conclude that serial production made no sense. The Germans limited themselves to 2 units, Schwerer Gustav and Dora, but neither saw mass employment. After Sevastopol, attempts were made to use the guns against Leningrad and at Stalingrad, but the front situation prevented these plans. In the end, no new orders were placed. Krupp proposed improved variants and even more powerful artillery projects, but the Third Reich's leadership placed its bets on other wonder weapons, V-rockets, jet fighters, and submarine technologies. Ultimately, the final decision to halt production was dictated by strategic inefficiency. Resources and time invested did not pay off. The effect of a few destroyed fortifications didn't match the price paid in diverted resources, lost time, and logistical difficulties. Military experts pointed out that a single heavy air raid could achieve greater effect at lower cost. As Germany shifted from offense to defense and the front demanded mass, mobile armaments, continuing the supergun program looked pointless. Thus, Dora remained a unique engineering record and a symbol of the era's technical ambitions, but in real combat practice its history proved that colossal firepower without regard to logistics, mobility, and war economics brings no strategic benefit. The decision to cease production was a logical step reflecting the hard necessity of focusing on more rational and effective means of warfare. By the end of World War II, the fate of the super-heavy railway guns Schwerer Gustav and Dora was tightly bound to the overall collapse of the Third Reich. By 1943-1944 it was already clear that such cumbersome systems had lost all practical meaning. Germany had moved to the defensive, the front was receding both westward and eastward, and Allied air power dominated the skies. Moving and protecting the supergun had become practically impossible. It is known that the guns were kept in reserve for some time. Gustav was located near test ranges and rear bases, while Dora, according to various reports, was dismantled and partially evacuated from the Leningrad area but never employed. In 1945, during the retreat, the Germans attempted to destroy the guns to prevent capture. One was blown up by its own crew, the other was seized in fragments and later scrapped. None survived intact, though individual parts, such as barrel sections or shells, have been preserved and are displayed in museums. Post-war historical assessment turned Dora into a kind of engineering record. At that time it was the largest caliber gun actually used in combat. Its characteristics, 800 mm caliber, shells up to 7 tons, installation weight over 1,300 tons, entered the textbooks of engineering history. But at the same time Dora became a classic example of how a technical marvel can turn into a strategic dead end. It showed that an excessive bet on a wonder weapon results in colossal costs and minimal practical returns. In cultural memory and popular imagination, Dora took its place alongside other legendary wonder weapons of the Third Reich. In books, documentaries, and video games it often symbolizes German tendencies toward gigantomania and technical extremes. Its silhouette, an enormous railway platform with an endless barrel, became a recognizable image in pop culture. Museum exhibits devoted to artillery history often display models, drawings, and photographs of Dora, while preserved shells and parts are prized artifacts. Dora's legacy lies not only in the engineering record but also in the lessons learned by military thought. In the post-war period it became evident that the future belonged to mobile, high-tech means, aviation, missiles, and precision-guided munitions. The concept of super-heavy artillery was definitively recognized as futile. Military analysts and engineers used Dora's experience to illustrate that gigantic systems without mobility and flexibility become not weapons but burdens. Thus, the end of Dora's story symbolizes both the close of the siege artillery era and the transition to new types of armaments. Its legacy lives not in practical warfare, but in memory, on the pages of books and in museum halls, where it is perceived more as a monument to engineering ambition and a symbol of illusory faith in wonder weapons than as a truly effective instrument of war.